So now let's proceed. So if we subtract the the unit weight of water from the saturated unit weight of the sun, what we'll get is the effective unit weight or the buoyant unit weight of the sun. So that would be equal to 19.25 minus 9.81. So that would be equal to 9.44 kilonewton per cubic meter times the height x, or the height of the groundwater table. So calculating or solving for x, we have 17.4929 meters. And we are asked to determine the rise. So the rise is equal to the calculated 17.4929 meters minus the previous or the existing groundwater table, which is 13 meters. So the rise would be equal to 4.4929 meters. So let's proceed to example problem 6.3. So a 9-meter thick layer of stiff saturated clay is underlain by a layer of sand. So the sand is under artesian pressure. So calculate the maximum depth of cut H that can be made in the clay. So how are we going to determine the maximum depth? Now we'll incorporate the idea of the quicksand condition. So our effective stress the effective stress at point A is equal to 0, and so we can now solve for H. So again, that is the maximum cut or maximum depth we can go for H before the soil will heave. So for the soil to heave, the effective stress at point A should be 0. Okay, so we have 0, or the effective stress at point A is equal to that is equal to the saturated unit weight, which is 18 kilonewton per cubic meter times 9 minus H, because we are considering this one. So this is 9 minus H minus the pore water pressure, which is equal to the head loss. Uh, 3.6, so equal to this one, 3.6 meters times the unit weight of water, which is 9.81 kilonewton per cubic meter. And solving for H, we get 7.0380 meters. Next example problem. So a bit similar, but it has a free water surface here. So a cut is made in a stiff, saturated clay that is underlain by a layer of sand. What should be the height of water H in the cut so the stability of the saturated clay is not lost? In the previous problem, we are asked to determine the maximum depth of a cut, and now in this problem, we are asked to determine the height, the minimum height of water to um, to maintain the stability of the saturated clay. So again, our effective stress at point A should be equal to 0. So writing the equation, we have 0 is equal to the saturated unit weight of the soil. So we have 19 kilonewton per cubic meter times this depth. So that is equal to 2 meters. Plus this one. So this is equal to H times 9.81 kilonewton per cubic meter. H is in meters. And also the pore water pressure. So that would be equal to 4.5 meters times 9.81 kilonewton per cubic meter. So solving for H, we get 0.6264 meters. So this part here is the total stress, and this part is the pore water pressure. So again, your effective stress is equal to 0. Now we're down to the last example problem. So a soil profile is shown below, and the heights of the different layers are also given. Now we are asked to plot the variation of the total stress, the pore water pressure, and the effective stress with respect to the depth. Okay, so before we can plot the variation of the three stresses, we'll first have to determine the values of those stresses. But before we can compute that, we have to get the dry unit weight, the moist unit weight, and the saturated unit weight in these levels. So this one, we'll have to determine the dry unit weight. So gamma sub d, again this is equal to G sub S times the unit weight of water all over 1 plus E. So this is equal to 2.65 times 9.81. I will be omitting the units so that we can save some space. And 1.5. And then this is equal to 17.3310 kilonewton per cubic meter. For the moist unit weight, or at the zone of capillary rise, we have we'll only multiply this by the we'll only have to multiply the dry unit weight by the 1 plus the moisture content. But before we can do that, we'll have to determine the corresponding moisture content at 50% degree of saturation. So we'll use the formula specific gravity times the moisture content is equal to the void ratio E times the degree of saturation. So this is equal to 2.65 times moisture content is equal to 0.5 times 0.5. And we'll arrive with a moisture content which is equal to 0.0943. And then the moist unit weight is equal to 17.3310 times 1 plus 0.0943. And our moist unit weight is equal to 18.9660 kilonewton per cubic meter. And lastly, for the saturated unit weight of this soil layer, we have we can use the formula gamma saturated is equal to the specific gravity plus the void ratio times the unit weight of water all over 1 plus E. So we'll have to determine the void ratio of this one. Again, we'll use this formula. So 2.71 times 0.42 is equal to E times 1 because it is fully saturated. And then we can get E is equal to the void ratio E is equal to 1.1382. And then the saturated unit weight can now be computed. So 2.71 plus plus 1.1382 times 9.81 all over 1 plus E, which is equal to 2.1382. And this is equal to 17.6554 kilonewton per cubic meter. So at point A, Obviously, our total stress, um, for water pressure, and effective stress at point A is equal to 0. So let's proceed to point B. So at point B, so our total stress, sigma B, is equal to 17.3310 times height h sub 1, which is 1.83. This is equal to 31.7157 kilonewton per cubic meter. While for while for the for water pressure at B, we'll have to consider the immediately below and immediately above point B. So now point B, the pore water pressure is equal to 0 for immediately above. While for B, this is equal to negative 0.5 times 9.81 times 0.91. So this is equal to negative 4.4636 meters. So immediately below. Therefore, we'll have two effective stresses. So sigma B prime for immediately above. So this is equal to 31.7157 kilonewton. Sorry, this is in square meter, per square meter, not cubic meter, because stresses. Yan, kilonewton per square meter. So this is above. I've also wrote the note above here because if you cannot read the subscript here, A. And while for the effective stress at B, which is immediately below, we'll have 31.7157 minus 4.4636. So we'll have the value 36.1793 kilonewton per cubic meter. So let's have point C. So we have the total stress, sigma C. This is equal to 17.3310 times 1.83 plus the moist unit weight, which is 18.9660 times 0.91 plus no more. So since we are already at 0.C only, so this is equal to 48.97. Again, this is in square meter. 9748 kilonewton per square meter. And this is below. So for the pore water pressure at sea, this is equal to 0. And then our effective stress at sea is therefore equal to 48.9748 kilonewton per square meter. And lastly, for point D. So we have the total stress, sigma at D, that is equal to, let's just copy, 48.9748 plus, so because this is the total stress at sea, we only have to add this one. So we have H3, which is equal to 1.83 meters times the calculated saturated unit weight, 17.6554 kilonewton per cubic meter. So total stress at point D, that is equal to 81.2842 kilonewton per cubic meter. Sorry, square meter, not cubic meter. And then for the pore water pressure U sub C, we only have 1.83 times 9.81. So this is equal to 17.9523 kilonewton per square meter. And lastly, we have the effective stress at point D. So this is equal to 81.2842 minus 17.9523. So this is equal to 63.3319 kilonewton per square meter. So let's remember these values. This one. Point A, the total stress at point B, these two pore water pressures at point B for immediately above and for immediately below, And these two effective stresses for the immediately above and immediately above point B. So again, the total stress at C, the pore water pressure at C, and the effective stress at point C. And then, yeah, similarly for D, the total stress, the pore water pressure, and the effective stress, which are equal to 81.2842 kilonewton per square meter, 17.9523 kilonewton per square meter, and 63.3319 kilonewton per square meter, respectively. So now we can plot, and your plot would look like this. So this is our plot. So this is our plot for the total stress. You can see that is equal to 0. All three. So the total, the pore water, and the effective stress are all equal to 0 at point A. Now for point B, we have these values which we have determined earlier. So this one is the for the immediately above, and this one is for the immediately below. Sorry, immediately above and immediately below. Immediately below and immediately above, rather. And this one should not be confused by this one because this is the depth. And yeah, so this one also. This will be our effective stresses. And then, yeah, so for point C and point B, the graph will look like this one. So that's it. We're already done with the first part of our 6th chapter in soil mechanics. I suggest you do some further readings in this book, Principles of Geotechnical Engineering by Braha and Das. And also practice solving problems, especially those problems that I have included in the learning management system. So that's it. Thank you. Thank you for joining me in another lesson, and please subscribe to my channel and hit the notification bell so that you will be notified whenever I will be uploading new videos. So bye guys, and see you in the next video.